To meet the post-war surge in transport demand, plans were discussed to strengthen the Takeda main line, and debates on quadruple tracking and construction of a high-speed new line became active. Fundamental reinforcement was deemed possible only by building a standard-gauge high-speed new line, prompting various studies into the optimal railway configuration. A train capable of cruising at an unprecedented 200 to 250 km per hour was required. Even in the rail-advanced nations of Europe and North America there were no such examples, forcing Japan to develop it independently. Although diesel trains in short formations had recorded speeds over 200 km per hour, their commercial operation was limited to around 160 km per hour. In electric service, current collection issues kept speeds at a comparable level. This was the world's conventional wisdom. Overturning that consensus demanded innovative technological development, and Japan's industrial capacity exhausted by defeat seemed incapable of realizing it. Fortunately, post-war JNR and private shipbuilders provided re-employment for former military engineers, creating an environment where stranded advanced technologies flowed in en masse. Thus, the era's cutting-edge machinery, electrical, and communication technologies were harnessed to pursue the dream of high-speed rail. In resource-poor Japan with weak diesel technology, electric traction was the only viable choice. To satisfy the surging Takeda demand with high-capacity, high-speed transport, development of electric trains exceeding 10,000 horsepower was required, so studies began with electric systems. The DC system faced the bottleneck of high-current transmission. Under the 3 kV DC electrification planned in pre-war bullet train proposals, powering a 7,500 kW trainset would demand currents well above 2,500 A when accounting for efficiency. Overhead and feeder lines would have to be substantially thicker, and numerous substations would be required to prevent voltage drop, sharply driving up electrification costs. At that time, AC electrification, which enables high-power delivery at lower current, was attracting worldwide attention, and Japan commenced full-scale research into AC systems. The challenge then became how to handle this high-voltage AC on board. As introduced in other videos, various methods AC commutator motors, induction motors, onboard rectified DC motors were tested. Initially, the AC direct drive approach using AC commutator motors capable of driving vehicles with reduction gears alone, similar to conventional DC series wound motors, garnered attention for its lower technical difficulty. A locomotive-based scheme was also considered, and since freight demand was soaring, freight locomotives were planned even for the high-speed new line. A high-speed locomotive rated at 13,200 kilowatts, one of the world's largest if realized, and 5,000 kilowatts for passenger service were studied. However, locomotive operation with 16-ton axle loads proved impractical. Construction costs, including trackbed reinforcement, became unavoidable, and the industry shifted toward low axle load EMUs. EMUs were also slated to adopt the AC commutator motor method, and by tailoring the transformer windings with a technique called overtap, field weakening control became unnecessary, simplifying the overall control system. This approach looked very promising. A 170 kilowatts motor was built, and mass production was within reach. However, AC commutator motors share the same basic structure as DC series wound motors. Commutators and brushes are unavoidable where parts end on an EMU carrying many motors. Maintenance became a serious bottleneck. Moreover, as an AC-driven machine, induced currents arise in the armature winding, and since brushes short adjacent commutator bars, heat generation and arcing increase, accelerating wear and fouling inside the motor. The onboard rectification method had the advantage of using proven DC series wound motors, but at the time rectifiers were mercury arc rectifiers, large, delicate like vacuum tubes, and requiring strict temperature control, far too costly, high maintenance, and space-consuming to install in every car. Against this backdrop, long-established induction motors came into focus. Induction motors have no wear parts other than bearings and produce little rotor heat, making cooling easy. And whereas a typical DC motor is rated below 1 kV, induction motors can handle up to about 6 kV. If the catenary were energized at 6 kV, the heavy transformer often cited as an AC EMU drawback could be omitted. Both infrastructure and rolling stock costs would drop significantly, making it an attractive simple electrification method for local lines. To exploit these benefits, various schemes were tried to propel vehicles with induction motors, whose speed can't be directly controlled. Two prototypes, Kumoya 7901 with a bicycle-style planetary gearbox plus fluid coupling, and Kumoya 79011 equipped with a hydraulic transmission were built and tested. Because the mechanical gearbox couldn't be scaled to high power, it was only suitable for simple electrification stock. Using induction motors on trunkline EMUs left hydraulic transmissions as the only viable option. Yet hydraulic transmissions faced a serious drawback: efficiency plummeted in the high-speed range, as seen in Shenzhen line trials. As a motor speed cannot be controlled, a direct drive mechanism like in DMUs cannot be used. To adjust speed, the slippage of the fluid coupling must be used, incurring losses equal to the slip. However, among hydraulic drives there exists a pump and hydraulic motor arrangement free of that problem. It had been used for machine gun mounts, small turrets, and agricultural machinery, and more recently gained attention in motorcycles and Type 10 tanks. Hydraulic motors employ pistons with variable stroke mechanisms, delivering ideal torque, control constant output over a wide speed range. But because their drive section comprises multiple pistons and cylinders, the structure is complex. Although more efficient than fluid couplings, overall efficiency remained mediocre, and high-pressure operation demanded precision machining, making them prohibitively expensive at the time. Designs for prototype EMUs did incorporate this technology, but unresolved durability issues meant that hydraulic transmissions were deemed impractical for Shinkansen adoption. At the time, hydraulic transmissions with a 500 horsepower capacity for railway use were already within reach, and induction motors being widely adopted in industry offered the advantage of requiring few new development elements. In the DD13's hydraulic transmission, variable guide vanes were controlled to reduce high-speed torque drop-off and exploit the transmission's torque-boosting effect over as wide a speed range as possible. For Shinkansen use, the same hydraulic transmission scheme was adopted, and concrete studies commenced to determine if 200 km/h operation was feasible. Each motor was a 380 kW single-phase induction motor. Two were mounted underfloor like a DMU, driving the wheels via hydraulic transmissions and propeller shafts. The bogies were two-axle drive units, essentially a DMU configuration. This closely mirrored a previously envisioned diesel Shinkansen with two DML-30 engines, similar in output and drive arrangement. A 12-car set service weight was assumed at 600 t, estimated over 10% lighter than that imaginary diesel Shinkansen or Series 0 EMUs. Speed control was simplicity itself, just metering oil in and out of the hydraulic transmission. No complex resistor banks or transformer tap changers were required. By adding a regenerative hydraulic transmission, electric regeneration could even be achieved with almost no structural changes. With regenerative braking, electric brake resistors became unnecessary. Combined with induction motors, substantial weight savings were anticipated. The tractive effort curves were as smooth as the DD51's 3-transmission profile. Naturally, they trailed the DD51 at very low and very high speeds, but outperformed a conventional hydraulic transmission. Acceleration curves showed a balancing speed of 250 km/h on level track, on par with later Series 0 performance. Original documents plotted two tractive effort curves, rated and full throttle. At full throttle, balancing speed climbed to about 280 km/h. Shinkansen line trials included a mechanism to boost oil pressure to the hydraulic transmission, likely improving high-speed efficiency. Lacking detailed records, only the rated curve data are presented here. Had this EMU been realized, it would have delivered uninterrupted, jet-like acceleration from standstill to top speed. Breaking down to about 30 km per hour below which regeneration fails would remain exceptionally smooth, thanks to regenerative braking via the hydraulic transmission. At notch 1 of the master controller, oil injection into the hydraulic transmission begins. Torque rises smoothly in proportion to the oil volume, eliminating the jolts that were typical in electric vehicles of the time. If the aforementioned pressure-boosting mechanism was included, it was assigned to notch 2. Notch 0 maintained the state where the main traction motor was running but with no oil fed to the transmission. The main induction motor continued to rotate at synchronous speed while consuming almost no electrical power. A cutoff position was provided on the master controller, where the main motor was finally stopped. Since the main traction motor could not start on its own, it was started using a capacitor-type induction motor as a starter. This master controller with its unique configuration and control logic unlike any on conventional rolling stock was truly an oddity. Once the transmission was full, acceleration continued uninterrupted, gradually tapering per the transmission's torque characteristic. With the notch off, the motors kept spinning while oil bled out of the transmission, so drive force faded gently again, no jerk. Shinkansen line performance reports note that staff were highly impressed by these operating characteristics. It's likely that the control-related jerks and resulting discomfort seen in later Series 0 EMUs during acceleration and deceleration simply did not occur. Since it employed a hydraulic system, the sluggish sensation at startup as seen in the Series 0 was absent. Acceleration was smooth yet forceful enough to make standing passengers feel a slight backward pull. However, due to low output, acceleration declined rapidly with speed. Its balancing speed on a 10 per mile gradient didn't reach 200 km per hour, but it was on par with the Series 0. On the 20 per mile grade at Sekigahara, it achieved just over 140 km per hour, about 20 km per hour lower than the Series 0. Naturally, even all-stop services on the Shinkansen had limited express-level stop spacing, and with long consists creeping through 70 km per hour turnout restrictions, its high-low-speed acceleration couldn't be fully leveraged. In terms of acceleration from 70 km per hour, both this EMU and the Series 0 reached 210 km per hour in about 5 minutes with the hydraulic EMU slightly ahead. Though both had nearly the same output, the hydraulic transmission's poor efficiency was offset by weight reduction, yielding surprisingly good performance. Looking solely at startup acceleration, it rivaled the later Series 300, the first Shinkansen EMU to use induction motors, but as previously noted, its low output meant post-launch performance wasn't comparable. Still, the fact that such performance was achievable with a hydraulic system suggests why engineers at the time seriously considered a hydraulic Shinkansen, captivated by the potential of induction motors. Their passion to utilize the dream motor, the induction motor, was intense. As EMUs were on the verge of widespread adoption, these engineers desperately sought to reduce the maintenance burden of trains packed with traction motors. Beyond mechanical and hydraulic induction motor EMUs, more radical ideas emerged. One proposal suggested rotating the stator. At standstill, both rotor and wheels would be stationary, while the stator rotated at synchronous speed. When accelerating, braking the spinning stator would induce rotor rotation and drive the wheels, a use of induction motors that seemed utterly unorthodox, yet was seriously discussed. In the end, the rapid advancement of silicon rectifiers made the onboard rectification method mainstream in AC EMUs, sidelining these varied innovations. The system settled on the familiar use of DC series wound motors. Even back in the vacuum tube era, many engineers believed in the promise of silicon rectifiers. Tests with induction motor EMUs on the Shinkansen line were met with skepticism in Japan, but attracted considerable international attention. Japan's ACEMU technology, beginning with the Sensen line, evolving into the Shinkansen, and driving major advances in power semiconductor technology, owed much of its momentum to these early experimental pursuits. From today's perspective, with precise control over three-phase AC, some of those efforts may seem laughable. But at the time, engineers earnestly pursued the use of induction motors and had a research environment that welcomed such ambition. That climate of long-term, curiosity-driven research contrasts sharply with today's trend toward short-term, profit-focused innovation.